In this video, we are going to talk about exponential relations and also compare the graphs of linear, quadratic, and exponential relationships. Before we start comparing them, we are going to define an exponential relation, which is in the form of y is equal to a times b exponent x. Now, a and b are real numbers. B cannot be equal to 1 because if B is 1, then this equation becomes y is equal to A times 1 exponent x. We said before that 1 exponent any number is 1, so this becomes A, which is a linear equation. This represents a line which is horizontal and parallel to x-axis. And also B here, the base has to be a positive number. This is an exponential relation. Now we are going to start looking at the graph of different exponential functions, and hopefully we can find some main properties of these exponential functions. The first example, we are supposed to make a table of values and graph y equal to exponent x. For the table of values, we are going to find the y values for x equal to -2, -1, 0, 1, 2. When x is -2, this equation becomes 2 exponent -2. Remember negative exponents. We find the reciprocal and the exponent become positive, so this becomes 1 over 2 exponent 2, which is 1 over 4, which is 0.25. When x is -1, this becomes 2 exponent -1, which is the same as 2 exponent 1, 1 over 2 exponent 1, which is 1 over 2, which is 0.5. The next one is 2 exponent 0, which is 1. Remember, any number exponent 0 is 1. Then this one becomes 2 exponent 1, which is 2. And this one is 2 exponent 2, which becomes 4. Now we are going to go ahead and plot this. When x is -2, y is 0.25. So it's going to be a point here. When x is -1, y is 0.5, which is somewhere around here. When x is 0, y is 1, which is here. When x is 1, y is 2, which is here. And when x is 2, y is 4, which is here. Now if I draw a smooth curve through this one, I get a graph like this one. If you look at the graph, you can see that from left to right, y is increasing. So this represents an exponential equation which is growing. So this is a exponential growth. Also, you can see that here, if I compare it with y is equal to a b exponent x, a is 1 and b is 2. The next example is y is equal to 3 exponent x. Again, when x is -2, this becomes 3 exponent -2, which is 1 over 3 exponent 2, which is 1 over 9, which is going to be approximately 0.11. When x is -1, we get 3 exponent -1, which is 1 over 3 exponent 1, which is 1 over 3, which is about 0.3. with 3 repeating. When x is 0, we get 3 exponent 0, which is 1. Any number exponent 0 is 1. When x is 1, we get 3 exponent 1, which is 3. When x is 2, we get 3 exponent 2, which is 9. So let's go ahead and plot these values. When x is negative 2, y is 0.11. So it's going to be a point very close to x-axis. When x is negative 1 is 0.3. It's going to be a point here. When x is 0, y is 1. When x is 1, y is 3. And when x is 2, y is 9. Again, plotting a smooth curve going through these points, we get a graph like this. Again, going from left to right, the y values are increasing, so this represents an exponential growth function. The next example is y is equal to 1 over 2 exponent x. When x is negative 2, we get 1 over 2 exponent negative 2. If I distribute negative 2 inside the bracket, I get 1 exponent negative 2, 2 exponent negative 2. 1 exponent any number is 1. 2 exponent negative 2, I can write it as 1 over 2 exponent 2. But 2 exponent 2 is 4, so I get this one is 1 divided by 1 over 4, which is going to give me 4. If you divide 1 by 1 over 4, you get 4. For negative 1, I get 1 over 2 exponent negative 1, which is 1 exponent negative 1 over 2 exponent negative 1. 1 exponent negative 1 gives me 1, so it's 1 over 2 exponent negative 1 is 1 over 2 exponent 1, which is 2, and 1 divided by 1 over 2 gives me 2. When x is 0, I get 1 over 2 exponent 0. Any number exponent 0 is 1. When x is 1, I get 1 over 2 exponent 1, which is 1 exponent 1 over 2 exponent 1, which is 1 over 2, because 2 exponent 1 is 2. And the last one, 1 over 2 exponent 2 is 1 exponent 2 divided by 2 exponent 2. 1 exponent, any number is 1, divided by 2 exponent 2 is 4, which is 0.25. Now, when x is negative 2, y is 4, which is here. When x is negative 1, y is 2, which is here. But when x is 0, 1, y is 1. When x is 1, y is 0.5, which is here. And when x is 2, y is 0.25, which is somewhere very close to x-axis. Again, a smooth curve through these points is going to give me a graph which looks like this. Going from left to right, you can see the y values are decreasing. So this represents an exponential decay. The next part of the question says, describe the similarity and differences between the graphs. As you can see, I'm using decimals to compare the graph of 2 exponent x, 3 exponent x, and 1 over 2 exponent x. For 2 exponent x, the black graph is this one. The red one is 3 exponent x is this one. And the blue one is 1 over 2 exponent x. You can see that 2 exponent x and 3 exponent x are exponential growth, because from left to right you can see that the y values are increasing, and the blue graph represent an exponential decay because from left to right the y values are decreasing. Another thing you can see is that all of them, they have the same y-intercept, which is this point, which is 0.01. Another property which is similar between all of them is that they have no x-intercepts. The graphs never cross the x-axis. The y value cannot be equal to 0 for this type of exponential functions. The next question says, Ontario's population is projected to grow exponentially based on the relationship given by this equation. P is equal to 11 million times 1.0112 exponent n. P is the estimated population and n is the number of years after 1996. And this formula is valid until 2031. You're supposed to use technology to sketch the graph here. The reason we're using technology is the numbers we're dealing with. You can see that this number, 11 million, it's a huge number. When n is equal to 0, meaning when the year is 1996, remember, n represents the number of years since 1996. If n is 0, meaning the year is 1996, then you are going to have 11 million as your initial population. And picking that point on your graph is going to be a little bit hard. Although it's not impossible, but it's much easier to use technology. In this part, I'm plotting 11 times 1.0112 exponent x. I use 11 instead of 11 million with this assumption that whatever y value you see here is multiplied by a million. For instance, this one represents really 50 million, not 50. It is much easier to fit the graph on the display here. Now, when you plot this one, you can see that the y-intercept is 0.11. This means the initial value of the population at 1996 is 11 million, which is the same as making x equal to 0. Any number exponent 0 is 1. So 11 times 1 is 11, which is in fact 11 million. And you can see as you go from left to right, the y values are increasing, so this represents an exponential growth function. And also, the graph never touches the x-axis, so this means that there is no x-intercept, and the y-intercept is 11 or 11 million, and the graph is an exponential growth. The next example, we have a table of values which represents the frequencies of the 8 A notes on a piano. For example, A4, which is here, has a frequency of 440, or A0 has a frequency of 27.5 Hertz. We are supposed to show that the relationship between the A notes on a piano and their frequencies can be modeled using an exponential growth. To check if this table of value represents an exponential relation, I'm using Excel again. These are the A notes. These are the frequencies. I found that the first differences are the difference between the y values. For instance, 55 minus 27.5 is 27.5. 110 minus 55 is 55. 220 minus 110 is 110, and so forth. You can see that the first differences are not the same, so it's not linear. Now I'm going to find the second differences. 55 minus 27.5 is 27.5. 110 minus 55 is 55. 220 minus 110 is 110, and so forth. You can see the second differences are not the same, so it's not quadratic. Now I'm going to find the ratio of the frequencies. 55 divided by 27.5 is 2. 110 divided by 55 is 2. 220 divided by 110 is 2, and so forth. You can see that the ratios are all the same. So this represents an exponential relationship. Now to plot that table of values, I'm using Desmos, and this is the table of values here. Remember, x1 represents the A note, and y1 represents the frequencies. Now, if you plot the graph, it looks like an exponential relationship. And as you can see, when you go from left to right on the x-axis, the y values are increasing, so this is an exponential growth. The y-intercept is when the graph hits the y-axis, and it is equal to 27.5, which is the same as this value here. Now, if you remember, we said at the beginning of the lesson that an exponential equation, we are defining it as y is equal to a times b exponent x. We said that the condition is that, first of all, b has to be a positive number, and b cannot be equal to 1. Now, as it turns out, if b is greater than 1, then the graph looks like this graph here. And as you can see, when we move from left to right, the y values are increasing, and this represents an exponential growth function. So in general, whenever you see an exponential function, look at the base. If the base is greater than 1, automatically you know that this is an exponential growth. For instance, y is equal to 2 exponent x. Because b is 2 and is greater than 1, if you plot this one, and if you remember at the beginning of the lesson, we plotted 2 exponent x, this represents an exponential growth function. Also, it turns out that if b, the base, is between 0 and 1, then as we go from left to right, the graph, the y values are decreasing, and this represents an exponential decay. So again, when you see an exponential function, look at the base. If the base is between 0 and 1, then you know that you're dealing with an exponential decay. If the base is greater than 1, you're dealing with an exponential growth. The other property of an exponential graph is that the exponential graph of the form y is equal to a b exponent x, the y-intercept here is always equal to a. The reason is that the y-intercept is when x is equal to 0. So this becomes y is equal to a b exponent 0. B exponent 0 is 1, so this gives you a. Now, in this case, on the graph that we have, your a value is 1. So when x is 0, the y-intercept is 1. And as also you can see that there is no x-intercept here, meaning for no x value you can have y equal to 0. So exponential relation of the form y is equal to ab exponent x, they do not have any x-intercept, and their y-intercept is always equal to